Hey, in this video, we're looking at a comprehensive problem and of chapter 16.90. I want you to read carefully the data. Um, you can also pause the video to make sure that first you have a clear idea of how to go about solving this problem. The main point of this is to write down the rate law for this reaction. So the rate law expression, the most general expression, is written down at the bottom of this page. So I want you to look at this problem carefully. We're given 4 experiments, 4 initial rates, 4 initial concentrations for 3 different species, A, B, and C, the reactants. Think about how this problem is similar to what we did in class. Think about how it is different from what we did in class. Try to solve it with what you know, and if for some reason you get stuck, you can always come back and check the video. Okay, so our task is to write down the rate law. Remember that the rate law includes all the specific values for the exponents for each of the concentrations for each of the reactants that we have, and also the value, the numerical value of the rate constant. So how do we approach these kind of problems? Usually the easy way to do is we go find experiments that keep some of the concentrations constant while changing other, just one, if possible. Why do we want to do this? Because in that way, we ensure that if the rate is changing, it's only changing due to that concentration that it's being modified. Because the other ones are constant, they don't have an influence, a net influence on the rate of reaction. But if not, then what happens is that the rate changes only because of the concentration that is changing. So in all these type of problems, we're going to be using this one equation where m, the partial order of reaction with respect to one of the reactants, is equal to the log of a ratio divided by the log of another ratio. So it's log of the ratio divided by log of the ratio. The first ratio is between the rates, the initial rates of reaction for 2 different experiments. 1 and 2 here are labels that refer to the first and second experiments that we choose from the data. It's not always experiment 1 and 2, but the first and the second experiment that we're choosing. X in this case is the actual species that for which we're looking at concentration. And again, it's the initial concentration of that species in each of the experiments that we chose. So let's do first the partial order of A, or we can also say the rate order with respect to A. If you look at the data, choosing experiments 1 and 2 will keep the initial concentrations of B and C constant. So the fact that the rate changes from going to experiment 1 to experiment 2 is because A, the initial concentration of A, is also changing from experiment 1 to experiment 2. Then what we need to do is to write a rate law for experiment 1 and then the rate law for experiment 2. You can tell that it's exactly the same expression, but in this case, the only thing that changes is that we need to keep track of the labels. So on the first one on the top, it's going to be R1, A1, B1, C1, making reference to the first experiment. In the bottom, I have the rate of the experiment 2 equals K times concentration of A to the alpha for the second experiment. So it's going to be A2, B2, C2, etc. Okay, don't forget the exponents alpha, beta, gamma. So next step is we literally just take the values from the table and we plug them into this equation. What you're going to find is that in this case, these 2 factors here for B and C, beta, gamma, they're all the same in both experiments. So if we take the ratio, these 2 on my right are going to cancel. K also cancels because it's always the same rate constant. And then I end up with this expression in the bottom. So now my task is to find alpha, and for alpha, I take the log over the log of the ratios for the rates divided by the log of the ratios for the concentrations. When I solve this equation, I end up having alpha equals to 2. Now, up to now, we now know the exponent for A, so we can write the rate law up to what we know. That expression will be rate equals K, rate constant, times the concentration of A squared, times the concentration of B to the beta, times the concentration of C to the gamma. So we know that the partial order of reaction with respect to A is equal to 2. So what next? Well, we need to find beta, gamma, and K, the rate constant. The question is if there are any two other experiments that keep fixed two concentrations and vary just one. The answer, if you go back, look at all the data, there is no such a thing. But since I already know what the dependence of the rate is with the concentration of A, I can just use that value and substitute it in the equation and not worry about it because I already know what happens with A. So let's calculate the partial order of B. If we choose experiments 2 and 4, we keep C constant only and only C. And now we will have changing B and A. Okay? But it doesn't matter that both of them are changing because I know how to deal with A. I know that is A squared. So it's going to come up as a number and then I just can use it in the equation as what it is, a number. So just as I did before, I write the rate laws for both of the experiments, experiment 2 and experiment 4. They look the same except for the labels that I'm assigning for experiment 2 in the first case and for experiment 4 in the case on the bottom. So I do the same thing. I substitute, literally just take the values from the table, plug them in into these equations. Now I can notice that only the last term is going to cancel out when I take the ratio. When I take the ratio, only the values for C that are constant just go away because they cancel with each other. K cancels with each other. Now I cannot cancel the value for A, but as you can see, it's just a number. So I take this number and I divide it by this other number, or well, I take the number on the left and divide it by this other factor on the right. And when I do that, I end up with this expression, and that part on the left is actually going to be equal to 1. When I solve this for beta, I find the log of 1 is equal to 0, so all this expression is going to be equal to 0. So beta is 0. So that means that the rate is not affected by the concentration of B because B will be raised to the power of 0. Anything to the power of 0 is 1, so it will not have an effect on the rate of reaction. B does not have an effect in the rate of reaction. So now let's look at the partial order of C. We can write down the rate law with the information what we have so far. Now the rate is equal to the rate constant times the concentration of A squared times the concentration of C to the gamma. Notice that we have not included here B anymore because we know that B does not affect, the concentration of B does not affect the rate of the reaction. So in this case, it's a very similar situation like we had before. There's no such experiments where we can keep A constant while changing only C, but it doesn't matter because we know how to deal with A. A is going to come up only just being numbers. So if we choose experiments 2 and 3, those two experiments make C change. Experiments 1, 2, and 4, they all have the same concentration for C, so we have to pick the two that make C change. I write the rate laws as I just did before, and I know that in this case A doesn't cancel, but A is just a bunch of numbers. So whenever I substitute all the values and I use the formula log over log, the log of a ratio divided by the log of another ratio, when I solve that problem, I end up having that gamma is equal to 1. So the partial order of reaction for C is equal to 1. Now, the only thing that it's left is to calculate the value for the rate constant K. Remember that the rate constant, something that I don't want to forget, is that the rate constant is a constant value for the reaction at a given temperature. That's very important because it's the constant for the whole reaction. And that reaction, it doesn't matter if I did experiment 1 or experiment 2 or experiment 3 or experiment 20. In every single case, I'm running the same reaction. Yeah, I have different concentrations and all that, but in every case, it's the same reaction. So I'm expecting to have exactly the same value of K independently of the experiment that I'm using. So yeah, let's take any experiment of the ones that were given on the table to find the value of K. Let's try experiment 1. We write the rate law for experiment 1. So it's R1 equals K times the concentration squared for the experiment 1 times the concentration of C for experiment 1. I plug in the values from the table and then I solve for K. I find that the value is 0.326. Now the units, please check the units. I actually put the workout of the units in here. Make sure that you have the units. The overall rate of reaction in this case is 3 because the partial orders are 2 and 1. When I add them up together, it's equal to 3. And that will give me a clue also with respect to the units of K. So have that in mind. If I don't remember that, I need to go back to my book. I need to go back to my notes to make sure that I identify that, yeah, when the rate order of reaction is 3, then the units of K are 1 over molar squared times second. Just for the sake of the argument and for you to try, make sure that you attempt any other experiment, 2, 3, 4, and you will end up having exactly the same value of the rate constant. Try experiment 3, for example. Make sure that you find the same value for K. Let me know if you have questions.